Alright, so you can see some highlights on the screen, which means I started this video, didn't like what was coming out of my mouth, so I'm starting over. Section 4.4 is on OR probability problems, and an OR probability problem is a probability that involves doing a single experiment, like picking one card from a deck of cards or rolling one six-sided dice. What makes it an OR probability problem is there are multiple events that we might consider successful. Like if I pick a single card from a deck of cards, I might ask you what's the probability of getting a queen or a heart. So there's two ways that we can satisfy and successfully complete the experiment, picking a queen or a heart. Or if I roll a single six-sided dice, I'll consider it a success if I get a number greater than 3 or an even number. There's two ways that that can be successful, getting a number greater than 3 or getting an even number. It's one experiment, rolling one dice, picking one card, but there's kind of two ways we can consider the probability of success. Usually when we're doing an OR probability problem, they're really easy to pick out because usually you actually see the word OR somewhere in the problem. However, sometimes instead of the word OR, you might see the word at least. But I would guess most of the problems we're about to see today are going to have the word OR in them somewheres. Let me just do a problem that's not one of my examples. That's kind of a classic OR probability problem. I'll tell you the common mistake and how to keep from making that common mistake by using a formula that I have up on the screen that I haven't talked about yet. So let me make an OR probability problem. I'm going to do a single experiment. So let me make up a single experiment. A single card is picked from a standard deck of 52 cards. So there's the single experiment part of this. I'm picking one card. What is the probability that a queen or, and there's the word or, a diamond is selected? So this is a classic OR probability problem. It's a single experiment because I'm taking a single card from a deck of cards. It has the word OR in it. Let me show you the most common mistake. So what I'm trying to figure out is the probability that I get a queen or a diamond when I pick one card from a deck of cards. It's going to be real common if this was a test question for students to go through and say, oh, in a deck of cards there's 1, 2, 3, 4 queens. So they would count 4 for the 4 queens, and there's 13 diamonds. So there's 13 diamonds and 4 queens. If I add up the 13 diamonds plus the 4 queens, I'm going to get a 17 for the numerator. That's a mistake. I'll talk about why it's a mistake in a second. But a lot of students will do this if this was a test question. They'd put 17 in the numerator for the 4 queens plus the 13 diamonds. There's where the mistake is. And they put 52 in the denominator because when you're picking a card from a deck of cards, 52 is the general denominator because a card deck generally has 52 cards. This is wrong, and the reason it's wrong is because it counts the queen of diamonds twice. If I wanted to do this less efficiently, let me just do this a correct way, but maybe not the correct way that we're going to use in this problem. A correct approach is just to figure out the correct number for the numerator by using just common sense and listing out all the cards. So the cards that can be fine for this would be the ace of diamonds, the 2 of diamonds, I can't write diamond every time, the 3 of diamonds, the 4 of diamonds, the 5, 6, 7, 8, 9, 10, jack, the queen of diamonds, and the king of diamonds. That's 13 unique cards right there that need to be counted in this probability question. Now, if I want to add any cards that I haven't already counted that fit the other criteria, because to be counted here, you need to be a queen or a diamond. I've counted all the diamonds. I haven't counted all the queens, but I've counted a lot of the queens. I haven't counted the queen of hearts. I can't do spades so well. Haven't counted the queen of spades, and it gets worse, I think, when I do clubs. And I haven't counted the queen of clubs, but I've already counted the queen of diamonds. The flaw in making 17 in the numerator is if I physically try to list all the cards that classify as queens or diamonds, I only get 16 cards. I get the 13 diamonds, one of which is already the queen. I can't count this queen twice, and then I get 14, 15, 16 when I add the 3 extra queens. This probability should really be 16 and 52 because there's only 16 cards in the deck that are diamonds or queens. The queen of diamonds doesn't get counted as 2 separate cards. And if you counted 4 queens and 13 diamonds, what you've incorrectly done is counted the queen of diamonds twice. Let me reduce this by 4. 16 divided by 4 is 4. 52 divided by 4 is 13. It's kind of clumsy to have to list out the entire sample space every time we want to do an OR probability question. And most of the problems in this section, instead of doing this correct approach, I'm going to use another correct approach, which is using the probability formula. And in this section, the formula that we're going to use to do OR probabilities is this. The probability of event A happening or event B happening is a probability of event A plus the probability of event B less the probability of event A and B happening together. And for this particular problem, the formula approach would be this. I'll put words instead of those letters. I'll say the probability of getting a queen, which for me is going to be event A, or a diamond, will equal the probability of event A, in this case the probability of getting a queen, plus the probability of getting a diamond, less the probability of getting one card that's both a queen and, running out of room here, a diamond. And this will get rid of, this part will get rid of the overcounting. So for my formula approach, there's 4 queens in a deck of cards. The probability of getting a queen is 4 in 52 when you're picking one card. There's 13 diamonds in a deck of cards. The probability of getting a diamond when you're picking from a deck of 52 cards is 13 in 52. And then the probability of getting a card that's both a queen and a diamond is 1 in 52 because there's one card in a deck of cards that is both a queen and a diamond. I need to subtract that away. So my formula tells me to take the 4 queens plus the 13 diamonds, subtract the queen of diamonds, and mathematically this is going to be 4 plus 13 minus 1 over 52, and then that reduces to the 16 over 52, kind of out of room here, but that's still the same 4 over 13. So for the problems in this section, we're going to use this formula when it's more convenient. If you don't mind using, digging through the sample space and finding all the objects that meet the criteria, you could do some of the problems that way. Some of the problems in this section are kind of designed where you're kind of stuck using this formula. So I'll leave this formula handy, and I'll start doing some problems in the section. I guess I have the formula right here. So 1 through 4. One card is selected at random from a standard deck of playing cards. Determine the probability of, and then hint, use the formula. The probability of A or B equals the probability of A plus the probability of B less the probability of A and B. Here, it says for number 2, what's the probability that I get a red card or a black card? Well, let me do 1 because it's more interesting, I guess. So for 1, for the probability of A or B, what I'm trying to find, so find the probability of A or B. In this case, for your problem 1, you're trying to find the probability of getting an ace or a jack. And if I use the formula, I know that that's the same as the probability of getting a card that's an ace plus the probability of getting a card that's a jack less the probability of getting a card that's both an ace and a jack at the same time. Let me look through my card sample space to get each of the numerators for these fractions. I know that the denominators for each of these fractions is going to be 52 because the experiment is picking one card from a deck of cards, and a deck of cards only has 52 cards. So when I go to figure out what the numerator would be for each of the fractions, for the ace, I'm going to put a 4 in the numerator because a deck of cards has 4 aces. So the probability of getting an ace is 4 in 52. For the jacks, the probability of getting a jack is also 4 in 52 because there's 4 jacks in the deck of cards. You notice that when I fished through the sample space and found the aces and the jacks, there weren't any overlaps between the aces and the jacks like there were between the diamonds and the queens. And that's going to tell me something about the next probability. When I did the AND probability for my queen and diamond problem, I had a 1 over 52 because there was one card that was both in the group of diamonds and the group of queens. In this problem, the probability of getting a card that's both an ace and a jack is 0 out of 52 because there's no one card that is both an ace and a jack because this set of cards and that set of cards don't have any intersection. So my answer to this is going to be 4 plus 4 minus 0 over 52. That reduces to 8 over 52. And then I'm going to divide the numerator and the denominator by 4. And I'm going to say the answer for problem 1, the probability of getting an ace or a jack, 8 divided by 4 is 2, 52 divided by 4 is 13. I'm going to say it's 2 and 13. There's a word that we use when the intersection part of the OR probability has impossible or it's a 0. It's called mutually exclusive. These two events, the event of getting a jack or an ace, are mutually exclusive, meaning if you get one, you can't get the other. If my one card's an ace, it can't be a jack. If my one card's a jack, it can't be an ace. Whereas the queen and the diamond, those weren't mutually exclusive. If my card's a queen, it can also be a diamond. But here, mutually exclusive means if one happens, the other can't happen. So there's your problem 1. Let me flash up problem 3 and 4, and your problem 3 is going to be much like my my problem that I did with the queen and the diamond. So give problem 3 a go. If you do 3 correctly and you reduce it correctly, your fraction answer should be 4 and 13. I'm going to do problem 4, which is asking for a picture card or a red card. So it's asking me what's the probability that I get a picture card, sometimes we call those face cards, or a red card. That's the same as the probability of getting a picture card plus the probability of getting a red card less the probability of getting a card that's both a picture and red. I use a little symbol for and because I was out of room. Let me dig through my sample space and look at the picture cards and count them up. So I said jacks, queens, and kings are picture cards. And if I count these up, there's 3 picture cards in each suit. There's 12 picture cards that I just counted up right there. So the numerator for my first fraction is going to be 12. for the 12 picture cards out of the 52 cards. The denominator would be 52. The next fraction is going to be something over 52, and it's going to count the red cards. And for my red cards, there are 13 hearts and 13 diamonds. There's 26 red cards. So there's 12 picture cards and 26 red cards. The numerators of my fractions, of my first two fractions, are going to be 12 and 26. I have to subtract out any card that I counted twice, and it's easy when I'm looking at the sample space to see what I counted twice. I counted the Jack of Diamonds, the Queen of Diamonds, the King of Diamonds, the Jack of Hearts, the Queen of Hearts, and the King of Hearts. I've counted all those twice. So for the third fraction, I'm going to get a 6 in the numerator for the 6 cards that qualify as both a picture card and a red card. So the third fraction I'm going to subtract is 6 and 52. And now let me just do the math here. This is going to be 12 plus 26 minus 6 over 52. I think that's 32 and 52. It's dangerous doing math in my head. Now I'm going to divide by 4 and get 8 and 13 for my answer. So that's the first 4 problems. I used the formula, but I transformed the A's and the B's into words that fit the cards that I was searching for. The next 4 problems just want me to use the formula. So let me look at what's given to me in problem 6. You should be able to do problem 5. It says, what if the probability of A is 0.6, the probability of B is 0.8, and the probability of A and B is 0.5, then it says find the probability of A or B. This is super easy because I know the formula. It says the probability of A plus the probability of B less the probability of A and B equals the probability of A or B. I kind of wrote this backwards, but I'll deal with it. All I'm going to do is take the numbers that were given and plug them into the formula. And for the probability of A, I'm going to put 0.6. And for the probability of B, I'm going to put 0.8. And for the probability of A and B, I'm going to put 0.5. I'm going to leave the right-hand side the probability of A or B. And that's what I'm trying to find. It says find the probability of A or B. I think I can do this in my head. I think it comes out to 0.9. 0.6 plus 0.8 is 1.4 minus 0.5 is 0.9. My answer, I can write the just the number 0.9 or just 0.9, or if I want to, I could say the probability of A or B equals 0.9. When you go to do your problem number 5, it's also 0.9. What's the chances of that? 7 and 8 are similar, but a little bit harder. 7 and 8 want us to find different items. I'll work through 7 with you because it's a little different than 8. So 7, I'm going to use the formula, let me write it in a regular way, that the probability of A or B equals the probability of A plus the probability of B less the probability of A and B. Let me take what's given. What's given in number 7 is the probability of A or B equals 0.8. So on the left-hand side here, I'm going to put 0.8. I'm given the probability of A is 0.5. I'm going to replace the probability of A with 0.5. The probability of B is 0.6. I'm going to replace the probability of B with 0.6. And then it says find the probability of A and B. So I have nothing to plug in for the probability of A and B. That's what I need to solve for. It's kind of a messy one because of the minus in front of it. Let me combine these terms right here. 0.5 plus 0.6 is 1.1. So this gives me 0.8 equals 1.1 minus the probability of A and B. Let me minus 1.1 from both sides. This gives me negative 0.3 equals negative probability of A and B. That negative is really a negative 1 times the probability of A and B. And to get the probability of A and B solved for, I need to divide by negative 1 on both sides. On the left side, when I do the dividing, the two negatives come out to be a positive. And on the right-hand side, the two negatives cancel and I get a positive. Let me write the word down. And B. So my answer for number 7, I can either say 0.3, or if I want to, I could say the probability of A and B equals 0.3. Then both would be correct for problem 7. All right, so for 9 through 12, it's a different experiment. It's rolling a single dice. And when we roll a single dice as opposed to a pair of dices, the sample space of what could come up, the sample space for rolling a single dice is, you can get the numbers 1 through 6. So I want to do some OR probabilities. A single dice is rolled. Find the probability of getting an even number or a number less than 5. So the probability of getting an even number or a number less than 5 equals the probability of getting an even number plus the probability of getting a number less than 5 less the probability of getting a number that's even and less than 5. Each one of these fractions is going to have a 6 in the denominator because there's 6 elements in the sample space. The first fraction is going to have a 3 in the numerator because in this sample space there are 3 of the numbers that are even, 2, 4, and 6. The second fraction is going to have a 4 in the numerator because there's 4 numbers that are less than 5. Less than but not equal to. The third fraction is going to have any number that I've just counted twice. And I actually counted a couple numbers twice. I counted the 2 as both even and less than 4. I counted the 4 as both even and less than 5, should I say. So the numerator of the third fraction is going to be the 2 elements in the sample space that I've counted in both probabilities. I'm going to subtract 2 and 6. So this is going to be 3 plus 4 minus 2 over 6. And my answer to problem 10 is going to be 5 and 6. For problem 9, if you do it correctly, I also got 5 and 6 for my answer. Let's do another set of these. So for 11, if you pause the video and do number 11, I get 1/2 as a reduced fraction. For my number 12, I want the probability of getting a number greater than 5 or less than 4. That's the same as the probability of getting a number greater than 5 plus the probability of getting a number less than 4 less the probability of getting a number that's greater than 5 and less than 4. I'm going to do this by forming 3 fractions, and each of the fractions is going to have a 6 in the denominator. I'm going to recreate the simple sample space to get my numerators. So for the first fraction, the probability of getting a number greater than 5, there's only one number greater than 5, so I'm going to put a 1 in the numerator. The only number that classifies there is a 6. For the second fraction, getting a number less than 4, there's 3 numbers that classify as less than 4, so that probability is going to be 3 and 6. And for the last fraction, I'm looking for overlapping. Well, there aren't any overlaps here. There aren't any numbers that are bigger than 5 and less than 4 at the same time, so that fraction is going to have a 0 in the numerator because I haven't circled any of these numbers twice. When I add these up, I get 1 plus 3 minus 0 over 6. It's going to be 4 and 6, and I'm going to reduce that. And the answer I'm going to write for problem 12 is just the number 2 and 3. More card problems coming up. So more OR probabilities. I don't know why I have the cards separated, but I just did them. So 13, you've done something like this already, you should be able to do. Let me do 14. One card is selected from a deck of playing cards. Find the probability of getting a queen or a diamond. So the probability of getting a queen, or a red card should I say, equals the probability of getting a queen, plus the probability of getting a red card, less the probability of getting a card that's both queen and red. I'm going to form 3 fractions, and each of the fractions is going to have a 52 in the denominator. And I just need to fish out the numerators. So for my first numerator, I'm trying to find the probability of getting a queen, and there's 4 queens in a deck of cards, so the first fraction is going to have a 4 in the numerator. The second fraction is getting a red card, and there's 13 diamonds and 13 hearts. There's going to be 26 red cards, so the numerator of my second fraction is going to be 26. And then I look through and see if I marked any card twice, and I marked 2 cards twice. I marked the Queen of Diamonds twice and the Queen of Hearts twice, because those cards are queens and diamonds. The third fraction is going to have a numerator of 2. And when I go to figure out my answer, I'm going to go 4 plus 26 minus 2 over 52. That's going to be 28 and 52, and I'll divide by 4. 28 divided by 4 is 7. 52 divided by 4 is 13. The answer to problem 14 is 7 and 13. When you do your problem 13, I get, as a reduced fraction, I get 4 and 13. All right, so give 15 a go. If you do 15 properly, you get 2 and 13 as a reduced fraction. For my 16, I want the probability of getting a queen or a 2. That's going to be the probability of getting a queen plus the probability of getting a 2 less the probability of getting a card that's a queen and a 2. I'm starting to abbreviate a little bit. Each of these fractions is going to have a 52 in the denominator because I'm picking one card from a deck of cards. And when I go to figure out the numerator, the first fraction, because there's 4 queens, is going to have a 4 in the numerator. The second fraction, because there's 4 twos, is going to have a 4 in the numerator. And because the group of 2s and the group of queens don't have any overlapping like the queens and the red cards do, the third fraction is going to have a 0 in the numerator because there's no card that's both a queen and a 2 at the same time. So if I add these up, 4 plus 4 minus 0 gives me 8 over 52. And when I reduce this fraction, my answer to number 16 is going to be 2 and 13. I'll skip 17. I'll skip 18 and let you do 17. When I get a reduced fraction for 17, I wrote 7 and 13 for my answer. Actually, I wrote 28 and 52 before it. All right, we're getting close to the last kinds of problems, but we have maybe a couple more to go. So one marble, so it's a single experiment, is selected from a bag, and this bag has red, 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 4 reds. I don't really have a white. Let me do white, 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 5 whites, and 6 blues. 1, 2, 3, 4, 5, 6. So this bag of marbles has 4, 9, 15 marbles. When I do my probabilities, each fraction is going to have a 15 in the denominator. So one marble is selected from a bag that has, oh, and 2 yellows. Oh, I missed these yellows. I actually have a yellow, yellow, yellow. So I have 4, 9, 15, 17. My fractions are going to have a 17 in the denominator. What's the probability of getting a red or a blue? It's the probability of getting a red plus the probability of getting a blue less the probability of getting a marble that's both red and blue. Now each of these fractions should have a 17 in the denominator because there's 17 marbles to choose from. For the red numerator, there's 4 red marbles of the 17, so I'll put a 4 in the numerator. For the blue marble, there's 6 blue marbles, so I'm going to get a 6 in the numerator for it. And then for the and, because this group and this group don't overlap, when the groups don't overlap, like those cards, you get a 0 in the numerator. When the groups have overlapping, you get something in the numerator of the and probability. So here, this is going to be 0 and 17, and when I add these up for an answer, I'm going to get 10 and 17. For your problem 19, I get 9 and 17. Makes sense. Let me worry about 22. So 22 is a probability of getting a yellow or a blue, which is a probability of getting a yellow plus the probability of getting a blue less the probability of getting a yellow and blue. Let me just write down my sample space again. There were 4 reds, 5 whites, 6 blues, and 2 yellows. So my denominators were 17 for each of the fractions because there's 17 marbles in this bag. And for my yellow, I'm going to put a 2 in the numerator for the 2 yellows. For my blues, I'm going to put a 6 in the numerator for the 6 blues. And because these circles don't overlap, I'm going to put a 0 in for the and probability. And my answer for this is going to be 8 and 17. These are mutually exclusive events. You can't get one marble. If you get a yellow, you can't get a blue. If you get a blue, you can't get a yellow. For your problem 21, I write 11 and 17 as my answer. It's only 29 problems, so we're button up to the end. Yuck. So 23 through 26, the numbers 1 through 14 are placed on a piece of paper and thrown into a bucket. One piece of paper is randomly selected. So my sample space for 23 through 26 is going to have the numbers 1 through 14, because the numbers 1 through 14 were put on pieces of paper, tossed into a bucket, and then it's a single experiment, so a single number is pulled out. If I go to do 24, what's the probability of getting an even number or a number less than 8? Well, I know that's the probability of getting an even plus the probability of getting a number less than 8 less the probability of getting a number that's both even and less than 8. Each one of these fractions is going to have a 14 in the denominator because there's 14 numbers that I've listed here. Let me mark out the even ones real quickly for the first probability. My first probability is going to have a 7 in it because I just circled 7 even numbers. My second probability is going to have all the numbers less than 8. It's also going to have a 7 in it because there's 7 numbers that are less than 8. My third probability is going to have any number that's circled twice. I circled 2 twice because it's even and less than 8. I circled 4 twice because it's even and less than 8. And I circled 6 twice because it's even and less than 8. My third fraction is going to have a 3 in the numerator. So I'm going to get 7 plus 7 minus 3 over 14. I think that comes out to 11 and 14 if I haven't made any horrible mistakes. I feel like I might have. 7, 1, 2, 3, 4, 5, 6, 7, right? 2, 4, 6. I'm counting out. I guess that's right. It just doesn't feel right, but I guess it is right. All right, for your number 23, you also get 11 and 14 for your answer. Let's work through 25 and 26. Your 25, I get 6 and 7, which is a reduced answer. For my problem 26, let me just write down the sample space because it helps me do these or probabilities. For 26, I want to do the probability I get a number less than or equal to 8 or an odd. That's the probability that I get a number less than or equal to 8 plus the probability that I get an odd, less the probability that I get a number less than or equal to 8, and it's odd. Each one of these fractions is going to have a 14 in the denominator because there's 14 different numbers in that to be selected. For less than or equal to 8, I'm going to count any number less than 8 or equal to 8. I'm going to count all those 8 that I just circled right there. For odds, I'm going to count 1, 3, 5, 7, 9, 11, 13. I'm counting those 7. And for the and part, anything that I counted twice, I counted the 1 twice, the 3 twice, the 5 twice, and the 7 twice. Anything I counted twice needs to be thrown out. There's 4 that I counted twice. This comes out to be 8 plus 7 minus 4 over 14. And I get 11 over 14, and that doesn't reduce. Last group of problems. The letters in the word Mississippi. 1 M. 4 I's. 4 S's. And 2 P's are placed in a bucket, and 1 piece of paper is removed. What's the probability that I get? So let's just do 27 together. What's the probability if I put all these letters on slips of paper and place them into a bucket and pull one out? What's the probability that I get a P or an M? So the probability that I get a P or an M is the probability that I get a P plus the probability that I get an M less the probability that I get a card that's a P and an M. Let me do the P first. The numerator is going to be 2. The denominator is going to be 11 because there's 11 letters in the word Mississippi. For the numerator of the next fraction, the probability of getting an M, it's going to have a 1 in the numerator because one of the 11 letters are M's. The next fraction is going to have a 0 in the numerator because I haven't circled anything twice. These are mutually exclusive events. And when I add these together, I get 2 plus 1 minus 0 over 11. My answer to problem 27 is going to be 3 and 11. I don't like problem 29 so much, nor do I like 30. Yuck. So let me try this again. So M, 4 I's, 4 S's, and 2 P's. So for 30, what's the probability that I get a vowel or a letter that's before R? That's the same as probability of getting a vowel plus the probability of getting a letter before R alphabetically less the probability of getting a vowel and before R. So for a vowel, I is the only vowel. So this fraction is going to have a 4 in the numerator out of the 11. Before R, S is after R. For the before R's, M is alphabetically before R's. Each of the I's is before R alphabetically. S is after R. And the P's are also before R. So there's 1, 2, 3, 4, 5, 6, 7 letters alphabetically there that are before R's. And then for the last fraction, the denominator is going to be 11. The numerator is going to be any letter that I circled twice, and that's going to be the 4 I's. Those have been circled twice. So this is going to be 4 plus 7 minus 4 over 11. And my answer to problem 30 is going to be 7 over 11. For your problem 29, I got 8 over 11. Yeah, I think that's right. So that's the whole section. It was hopefully a friendly-ish section. For all the sections in Chapter 4, you should have them completely mastered before going on to the next section, just because you might start confusing yourself, because the problems will start to look similar, but they'll actually be different.